It's my pleasure to introduce the speaker, Wayne Daley, from Georgia Tech. Wayne and I met when I was at UGA, and we've had a few other. And I think the great thing that hopefully you'll see today is his excitement and his desire to look at in what the future holds in terms of poultry science. How can we be driving the movement of the industry? What are the things that we need to look at before the problems get here? How can we solve those problems? And provide resources that are here and now before we have to deal with problems there. Let's see. You know, I don't even know where you did all your graduate work, but now we know that you lived for 3 years on your grandparents' farm and required to slaughter chickens. So that pretty much makes you an expert in poultry science.
I should still know where I was going to end up.
Lots of hands-on experience.
Lots of hands-on experience. So, you know, he may be working with, you know, robots and computers, but he has gotten his hands dirty time and time again.
That's right.
So we'll
Okay.
give the
All right,
time up
okay,
there.
thanks, Robert. So, as Robert mentioned, I'm a researcher at the Georgia Tech Research Institute in Atlanta. And you can tell I'm really from the South. People down there think they're from the South, but they're not. So I was born in Jamaica, which is a little bit more south than most of the people down here. And but Robert is correct. From a certain point when I was growing up, I lived on a farm with my grandparents, and so I have a whole different view of livestock and animals and stuff. When you have to work with them, I think you have a whole different view of the world. But you know, at the time, never knew I would end up doing research related to those projects, but it's been good. I'm just having to for that you know, been at Georgia Tech a while, but you know, it's been at the same place, but it has not been the same job, but it has been enjoyable. So I'm going to try and talk a little bit about kind of some of the things we're doing at Georgia Tech and kind of where we see things kind of going. And it's meant to be kind of a conversation type of thing. If at any point you think you want to ask me something, stop, it's fine. And we're just going to be explaining some of what we're about, and then, you know, you just see where it goes. But in the end, like I mentioned, I think the takeaway is, I really think engineers need to understand more of the biology and the physical sciences and some of the things that go on there, that we can better tie that knowledge together to try to come up with solutions. Appreciate Robert inviting me up, and you know, appreciate the hospitality. We had dinner at Cantina 18, Cantina 18. So we had these tacos with craisins and goat cheese and chicken. And so I'm not sure the guys that came up with tacos had that in mind, but it was pretty good. Anyway, but thanks for the invitation, and appreciate you guys putting up with us. All right, so background, I'm trained as a mechanical engineer. Got all my degrees at Georgia Tech. And like I said, I had no idea I was going to end up working with chicken. But one thing that's kind of led to another, and you know, it turned out to not be too bad at all. So we're part of what's called the Georgia Tech Research Institute. And we do $300 million worth of research a year, something like that. And as you can tell from these pictures, we're probably a strange bird. Okay, does this thing have a point?
Very tall.
So you can see that most of the things we do. All right, and then you see us. So yeah, we you know, we're a little bit different. I mean, these guys are doing all that stuff with LiDAR and LADAR, laser rangefinder things. These guys are doing stuff within how you protect soldiers that have to, you know, go do things that you usually don't want to be messing with. There are people here that are working on cybersecurity type issues. These guys actually do modeling to protect, you know, aircraft and stuff from people that might want to shoot them down for different types of reasons. So these are little actual devices. They detect that somebody's trying to shoot them down. They fire these things to try to, you know, act as a decoy. And these guys are, you know, experimenting with swarming autonomous vehicles. So you put 20 of these things And you tell them to go do something and you just let them go, they go do what they need to do and come back. All right, all kind of autonomous. Then you have others. But it turns out a lot of these technologies and stuff we use here, we can leverage for some of our problems. And some of our people actually do a lot of work in these areas because they use robots doing some of the things they do. They use autonomous things in some of the things they do. So we try to leverage where we can. Okay. And these guys usually have a heck of a lot more money than we do. So wherever we can beg borrowers to do that. But so that's GTRI in a nutshell. Dr. Laura Rice is the director, and they report up to Dr. Peterson, who is the president of the church. We're in a lab called ATAS, which is a Space and Transportation Lab. GTRI has like 8 labs now, I think. And so how did we end up in the Aerospace and Transportation Lab? The only explanation is that chicken has wings. That's that.
Wow.
But we'll go with it. That's my explanation. But like I said, though, it's been a good collaboration working with an institute. And then the other thing behind Georgia Tech is that you also have access to the faculty, right, in the rest of the school. So if we're doing something that we don't have expertise or experience in, there's usually somebody there that knows, and so we can make those connections. When it comes to animals and that type of stuff, we go to Robert's old home, and so we have close relationships with the guys over at UGA in terms of doing experiments and some of the things you do. We have actually done experiments over there in Athens. All right, so that's a little bit of the groundwork. So this is just meant to show some of the different things we have going on in the group. We'll talk a little bit about some of the robotics work today. And this is robotics related also, but we're also doing different ways of sensing in these environments. We are also, this is robotics related also, but it's something of collaborative robots, where we're looking at robots that can work with people. And then this is me, and this is Casey Rich at the University of Georgia. So I've been running this audio project where we're trying to record birds to try to tell something about their condition. Then my project in food safety, environmental research, separation technologies is an effort to look at how you could separate things in the waste stream. And then Jay here is doing a lot of work with the nanoparticles and those types of technologies for a variety of applications. So this kind of just gives the overall picture of some of the activity in our group. So our vision for the group is working with others and working with the team. We are trying to transform poultry and agribusiness in the state of Georgia, right, through the use of advanced technologies. So part of our strategy is to kind of keep our fingers on the pulse of what's being developed, what's there, and what can be leveraged, address some of the issues that we know are coming around, coming down the pipe. And the program is funded, like I mentioned this morning, since poultry is such a big part of the state's economy, to the tune of $13 billion, I think, and you add up all the ancillary products, the state funds the program to look at challenges or issues that industry brings to it. So most of this work is done under this agricultural technology research program. We have a 4-part mission in HRP, but most of this revolves around the research, but we do have a small education function, we do some outreach, and then technology assistance. Companies can call us, and if it's a quick question in a day or so, a couple of the engineers are available to probably try to assist. But most of the resources go towards the research. So we're looking at robotics in the spectrum of activity. Okay. Currently, our work spans from grow out through first and second processing. Is where we currently have activities ongoing. I have a video in here. I'm not sure how to do it. Okay. So this is our grow out house robot, is what we call it. We see probably a layer house is probably one of the first places where we might apply this thing. And so, this basically will drive through this house through some prescribed paths. We'll try to avoid the chickens. And this is a device running in our place. So we'll have a prescribed path here, and what it's doing is basically going to these places we told it to go to. But this is similar to how it operates in a house. And so we anticipate these devices ever so often will just kind of, you know, make a circuit or go through the house. And then as we're thinking about it, then you probably wouldn't want this thing running up at 500 foot, 200 foot house all the time. So we think you probably have these little devices that might go through and scan to kind of see if there are issues. When it's done, it would then let this device know where those issues are. And in this case, you know, when these X's that it had found. So this thing will then go to those things and do whatever needed to be done. So it might have spotted a dead bird or an egg or something. So this device will then go to these places and kind of do what it needed to do there. And so the thing is it's dynamic. Anything, the obstacles, it detects them and it tries to avoid them, right? No matter what happens. Either they're fixed or moving, the machine will try to avoid them the best it can. And it's kind of mapping this environment, so it's kind of knowing where things are and that kind of thing, right? But the idea is it needs to be able to somewhat dynamic, assuming the environment is going to change around it. And if you have chickens running around and stuff, then it needs to happen. So we spend a lot of time trying to get that to work. And then one of the things we think it might do, especially if we're in a layer house, is the ability to go pick up eggs. And so we've programmed it to try and find an egg, and, then go pick them up. We'll put them in a little carrier, and then when it's done, it will take them somewhere that So this is our and so you're kind of moving. So we move from the grow house now. We're down now in processing, and this is one of the collaborative robots. So the nice thing about this guy is people can work around it. So if I came up to it, it would detect that I was there. You could either slow its motion down, or just warn me. So that if it hit me, it would actually stop and back off. A traditional robot wouldn't do that. And then the operation it was doing, there was something called cone loading, which is when you're deboning, the first operation of that thing is actually loading the cone. So even with the automated machines today, that's still a manual operation. And so that's one of the operations we're looking at, whether or not you can automate that. So, I'm sorry, I didn't get, do you remind your name?
Marilyn?
Melanie?
Mm-hmm.
Okay. And so one of the things we're looking at now is, is that maybe a potential application that we should target in terms of giving more resources to see if we get the product out there to go do something. Right? So, you're asking how we kind of decide which things to choose. So, we try to, well, is this going to have significant impact? Maybe. And we think we can get this to do the job, then we'll probably focus on more resources on that one. And then the other robotic thing we have going on is, and these are show some of the partners that we work with. So then after you load the cone, this is the wing cut we talked about, right? And so imagine kind of doing it all the time, 8 hours a day. But you see we have a model of the skeleton, and then what we actually do is we actually sense this bird, and then the robot will then actually go in and try to make that wing cut. And this is it trying to do it online. So we did this with this fairly expensive and fairly big robot. So this is another application we're looking at porting now, and so we've actually ported this now, or we're in the midst of porting it to a much smaller, faster robot, all right? And then we're going to have 2 of them working on the line, just like you saw those workers, and we're going to try to see if we can get those guys to do the wing cuts, at the line speed. All right? So that shows you the spectrum of what we're kind of trying to do with our robotics kind of effort at this point in time. And again, so we develop a model for the skeleton, and we do this by measuring some of the external features, and we have some algorithms that allow us to then estimate where these trajectories need to be. Okay. So, go sure.
On that model, I'm assuming there are different laser type probes that can pick up different tissues and bone and so forth. But is it possible to scan the carcass with some type of laser, and then that goes into a database and tells the knife where to cut, without having to do the modeling on, say, assuming they're all the same size or something like that, can actually map the carcass and cut it using some sort of sensor?
So, I'm not sure we're doing it exactly that way, but your point is we should be doing it for each bird.
Yes.
Right. And so we are doing it for each bird, but we have an algorithm where we sense the outside, we have a couple of key points we pick up, and knowing those, we then have an algorithm that generates these cut trajectories. But it's doing it for each bird.
Okay.
Right, and it's trying to adapt for it, right, you know the problem.
So then so for the way you cut versus a human, what's the difference in productivity or waste loss or?
So the preliminary tests say we're as good as probably the best average guy.
The best average guy.
But we're gonna run for 8 hours at that level. He's like this. After 2 hours, I mean, we've gone in there, and after 2 hours of doing this, you're not doing as well as you did when you started it. 10 o'clock, you're not where you were at 8. So even though we may not be as good as the best, we think we're going to be more consistent. And overall, that's going to work out a bit better. So our view, though, is that chicken is going to continue to be a significant source of protein.
Sorry for
No,
disturbing.
that's fine.
Question I have is, this robotic system, is it going to be the first of its type in the world?
I don't know anybody else that's currently doing the
Now,
with the
before you
robot.
decided to go for this robot, and I know it's a step up, did you think about the kind of setup that surgeons use for microsurgery, where they look at it and they just have to move stuff around and surgery happens somewhere else? Did you actually?
Yeah, but that's you know, like, well, some of the teleop systems or some of the robotic systems they have now. But you still have to sit there and do every one. Right? Somebody still has to sit there. You might have a little bit of an assist now. And we've thought about that, but in terms of being an assist, can we get these guys to do 90%? And then maybe if there's a 10% issue, you have an interface where somebody can go take care of that 10%. But, you know, we're doing, a line is what? A kill line is 200 birds a minute, right? And I think by the time they filter them down, each of these lines are running 30 some odd a minute per person. So, you know, a surgeon, you know, had a procedure done the other day and it took him 2 hours, right? These guys have to be done in 2 seconds, right? So yeah. Very difficult way to do it. But anyway, our view is our chicken is going to continue to be a significant source, mostly because of the work you guys did, right? I mean, you guys have seen all this stuff, right? Significant in terms of what we've been able to do. And then if you look at all these other sources of protein, I think chicken still has its smallest footprint in terms of environmental impact, right? So we anticipate that it's going to continue to be a significant source. So I think we need to continue to do what we're doing, see how we can make it as efficient as we can. But as I said, most of these benefits has been to, I think my understanding is from the genetics, what they've been able to do there, and from the nutrition, right? The increased knowledge and how well those things work. And so it shows here, right? If you look at what has happened, decrease in growing time, feed efficiency, percent mortality, everything, right? Everything is kind of flattening out now. So we need to figure out what's the next generation of change that's going to improve that, right? And so we have to tell this to a lot of people, because the people that we work with half the time, that's the first thing they ask. So how much hormones are they putting in the chicken? None. How many steroids are they? None. So this is a question we have to answer all the time, so that's why this is here. So these are traditional measures, but we think the game is changing, like I said. And so there's some other drivers that are now being significant, right? Food safety, well-being is just a significant one that we're still trying to figure out exactly how we respond properly to it. Labor is the other huge guy, which drives the robotics work. And the environment, right? We've got to make sure that whatever we do is somewhat sustainable. And so those are the things that we think are going to drive what we need to do in the future. And we're trying to figure out how best we position ourselves to try to address these questions. So the thinking is that, we've done a pretty good job actually, from the Industrial Revolution to some of the things we've been able to do with physics and all the electronics that we have now. I'm fortunate, right, because I've actually gone from programming computers with punch cards,
Yep.
all right, to seeing what we see now, which, most of the kids have no idea what it is. There's some kids now that, my kids didn't even know what an LP was. I mean, I had them in the house, and they were just so intrigued when I got some of them and started to play them, because I still had it, but they'd never seen them. And some of them now don't even know TV. All right, just to tell you. All right, so it's been amazing what's been able to, what's happened here. The thing though that to me is an issue is that we haven't solved a lot of the big problems, right, with this stuff. Most of this stuff is entertainment, right? So we can watch Netflix, and we can text, and we haven't touched a lot of the significant issues that we need to live, right? And so, but I think herein lies a lot of the answers. And part of the story I've been saying is we need to understand how we bridge these guys to tackle some of those real issues. Right? So I think it's going to be the integration of all these things, not just the biology, but these guys need to better understand what's going on here. And I think a better understanding here will enable, just the better guidance as to how we should move forward to try to look at some of these problems. So, as I do think it's the age of biology, and it's really kind of intriguing. I listened to people at dinner last night. We were talking about the Toro virus. That was that. What is it?
Toxemia, osmosis.
What's that virus?
Toxoplasmosis.
Toxovirus, not the pox. All these. So there are all these things that happen that to me are just amazing, right? And it seems like we don't fully understand how all those things do what they do, but it seems like we need to learn and leverage that. But some of the things we're doing is we are trying to see how we can do this. And some of this actually started with some work we did with Robert, where we actually did some scans. They were doing some scans for trying to understand surface area of a bird and how that might help them to dose medicines. So we took some of those and started to look at, well, maybe we could use them for some other things too. And So again, we try to leverage technology what you can. You saw that virtual reality headset there. So what we actually do is we take those CAT scans, we put them in a virtual reality system. And then we develop models for how you might do the cuts in the virtual reality system. So what you see here are actual cut trajectories, all right? And then we then put them in a simulator that simulates what the robot is going to do. You see the skeleton again, and you can see the knife, or virtual knife trying to follow the path you programmed it to do before. And so it first does the left and then does the right. But then we can simulate all this in this environment without even touching a chicken, right, other than doing the scan. And then we can actually now have the robot go through and do this all in simulation, right? So we can understand how it's likely to behave. Is it going to cut a bone? Is it going to touch anything? What's going to happen, all right? And then once we're comfortable, we can then actually just port this directly to the robot, and then we can try stuff. So we're trying to develop this development pipeline that allows us to try these different ways of doing it. So we develop the model, we do the CAT scan, we come up with a model, we come up with the cut trajectories, okay? And then we can then test it, and then we can actually go right to the robot and have it try to do some stuff. So this is kind of, you're looking at the state of the art. This is actually where we are now. So as I'm here talking to you, there's a guy now programming this same robot. And we're going to try to do a bunch of these cuts, probably by next week to see how well the thing works. But what we have now, though, is this pipeline that goes from the biology, right? We scan these things. We go talk to the physiologists. They say, well, really, the best way to cut it is to cut this first, then this, okay? And then you might want it to do this. And so in the virtual reality environment, and so this is where we leverage, right? Your kids are playing games with it. But that is a huge tool that can do a lot of other stuff. And I'm trying to tell my kids, you guys should just really understand what you can do instead of just running around shooting people all the time. There's other things that is useful. And but yeah, so we can go in there and you know, you can blow them up and you're walking around in the chicken, right? Yes. Oh, okay. So that's weird. Okay, so we want to do that and you create the trajectories. You come up with the models, we identify the points, come up with the models, and then we can just drive with the robot. So, but that process of going from the biology to the machine is what I'm talking about. And so it's been interesting working with the physiologists. You know, Jeff, over at USA Air, so Jeff, he's kind of a funny guy. So we had this idea maybe 6 years ago about trying to understand the biology before we're trying to do the manual one, right? We're teaching it manually. So I sent a note to Jeff. I said, Jeff, can you tell me what we need to cut? So he sent something back. He said, you need to get this book. So it's this big blue book, Avian Anatomy. And then he says, then you want to look at these pages and these slides, right? And this book had all these hand drawings and stuff in it. You guys know this book? I forget who wrote it. It's like that big blue. And so then we got stuck. And we came upon this thing now, and you know, we're back again now trying it. So I sent him a note. I said, Jeff, how do we cut this thing? So he sends a note back. The same note he had sent 6 years before. Pages and stuff highlighted in yellow. So, but you know, but he's a good guy. He's just, if you know him, he's just kind of dry wit, and that's just him. But the interaction has just been good because you know we are trying to understand just how these things are structured, how they work, and how what the machines actually need to do. Right? So, all right. So we're okay. Vertical environments. And then we're just trying to understand the biological and the physics that then has to, you know, allow us to do these cuts. So there's a lot of work, right? Because, you know, the kids have to figure out now how these robots, you have 6 joints on this robot, it looks easy. But if you have 6 joints on a robot, there's a myriad ways you can do a job. And so they have to figure out what's the best way and without causing the joints to do strange things and so on. So it's kind of an interesting mathematical problem for some of these guys. So this is actually from some of the work we did with Robert, and that this has to do. So we can make these measurements, and the question was, the initial question was, if the birds are in the house, right? Can we measure something? It's a bit like phenotyping. Can we measure something that could allow us to tell us something about some of the other structures on the bird? And so Robert tried. Maybe we could have measured the long toe, which was, if we could measure that, then you could imagine that robot driving around in the house. It could probably be measuring those things. Then if we could correlate that to different, you know, the humerus, the radius, we can then tell something about what those birds likely to look like and what the population likely to look like before you go to processing. And the correlations look pretty strong, right, in terms of trying to use that approach. But it's just another, you know, another thing of trying to understand the biology and how then you might use it, you know, in production and processing. This can lead to, you know, measuring conformation and just a whole host of things. We're not even sure where all of it goes. And then, so then it allows us also to start making things more quantitative fairly easily, right? So we always, you know, we want, for example, to measure bones. Well, the engineer said, well, how are you measuring it? Oh, we just kind of look at it and we pick this end and we pick this end and it's, you know, 2.5 centimeter. But that's not the end that you pick and the end that Ling picks, sometimes not the same. So, you know, how you know you get the right thing. But the engineers have some things that they do, so can we apply it? So, you know, they use principal axes. You give it the thing, it will always give you the same principal axis. Right? So you can then use that to measure the things. You can then compute stresses. If the animal is standing up and the weight is distributed a certain way, what are the stresses actually in the bones and stuff? So it allows you to start putting numbers to things, right? As opposed to, and then you can actually then make calculations and do your design. So those are some of the things we're trying to, like I said, going from the biology to the engineering. And so when we stopped the video on the egg thing, you know, I said, well, you know, to do pick up eggs and more. So we anticipate this device is going to have a full suite of sensors. You know, temperature, humidity, audio, 3D video, a whole host of things. And then, you'll be able then, this is a big data problem, because then you'll be able then to tell a lot of things. You could, for example, tell something about, so this is actually raw data of a chicken in a house. So you can actually now start to tell something about the shape and the conformation on the animal. To track it in motion, you might be able to measure something about gait, right? If you have all the audio, then, and we understand, kind of what that means, we might tell something about the well-being. So once you get these things in the house, you have a whole host of things we think are going to open up to you in terms of what you're able to do, okay? And you buy this device, right? I think the guy, what was different with this guy than other people? He didn't see this as a phone. The other people still thought they were building phones, right? But this guy, he saw it was no longer a phone. And he was going to give you other things on here that you could do. So we anticipate a similar thing is going to happen, right? Once you can get the thing in the house, and you can see what you have, people are going to think differently just about how they do what they do. But to make that jump, right, you got to make that jump somehow. You got to think about that. How does it happen? And people always talk about innovation. You need to be more innovative, and it's usually easier said than done. Right? And we have some good stories. Oh, so you saw those curves: feed conversion, flattening, mortality flattening. So this is typical the innovation cycle, right, or automation efficiency cycle. So usually you have some kind of a breakthrough, and it improves, and then after a while you improve on it, it just kind of flattens out. Then something new will come along. Usually though, when it starts out, its efficiency is below where you were before. And a lot of times, this is where the companies have a hard time. You come up with this new idea. Is it as fast as? No. Is it as cheap? No. So well, why the heck would I want to mess with that? All right? But this is where it is. But this is what's going to happen. It's the only way you're going to get up to the next level, right? Is to make an investment and work with it to get it up to the next level. And so we have to realize this is kind of what we're working with. Now you can't do everything, right? You're still going to have to pick the thing that you invest in. But we have to, start up realizing this is kind of where we are. And the new things are probably not going to be where they need to be. But you still need to invest in them, and you still need to work with them. So, innovation. So, this is this fellow's definition. Creation and better use of, better or more effective use of a device. So that people define what they call sustaining innovation, all right, which usually just means that you improve on something, right? You go from plain Cheerios to Honey Nut Cheerios, different type. You go from iPhone 5 to iPhone 6, and then it's disruptive type things, right? So this just changed everything, right? Horse and buggy, that just changed everything. Anybody, what's the company that used to rent the videos?
Blockbuster.
Blockbuster. Some of them probably even know Blockbuster was young guys. I have no idea who they were. So this is what it is, right? You kind of have to be thinking a little differently about how things are going to go. This one is interesting. So this is what the first digital camera looked like. 8 pounds, 100 by 100 resolution. Image was recorded to tape. All right? And then you have to display it on this thing. And so this company had this, right? And that's the most key thing in all of these things now. Everybody's doing selfies. It's a dang camera, right? That's the key thing in these devices. And these guys had it. They put it down. They did nothing with it. Had all the patents and everything. You know who it was? Kodak. Huh? Kodak. They built the first one. They had it.
So film oriented, they didn't want the digital to take over.
They were making too much money.
Yeah.
They were making money hand over fist. They were selling you paper, they were selling you chemicals, they were selling you cameras. It was tough for them to quit and do this. And it looked like this, right? So this is the thing with that curved thing sitting down here. Why? Why would you do that? Okay, well, somebody else, it was Kodak, and now they're out of business. Somebody else took it, called the patents, and they ran with it. Right? So that's, it's a technology thing, right? Sometimes you do this and the technology doesn't look good, but you got to figure out, you have a vision to see where it's going to go if you stick with it. Then here's a marketing thing, right? So this one is probably the most disruptive thing we've seen. There's one company that could have done it, though. Right? They had everything. I don't know if anybody can guess. The workplace, right? They had touchscreen technology in 1996, 2 years before. Historically, they were a very, responsive company, right? They were in the paper, they were electricity, they did all these things, and they got rid of it and went into telephones, right? But their problem was they're stuck on the button. They're seeing it as a phone. They're still, in their mind, they're still saw it as a phone, right? And they could not see getting away from that pad. You push the button. They just. But Apple took a whole different approach. They didn't see it as a phone at all. They saw it as some other device you're going to use, right? And he saw the broader picture. He started, giving you these other apps. The first thing he started was the music. And then he sucked you into the environment where you had to buy all your stuff from them, so he made it really sticky. Then he made other people, gave them the tools to build things around it, right? So he set us up. And so now we're all sucked in. We can't even leave home without it. All right? And I'm telling you, in Atlanta, I'm gonna guess 50% of people probably couldn't find their way home. They died. My kids, a friend of mine, she took her kid to high school, his sophomore and junior year, every day. He got his driver's license this summer, and then senior year he drove to school, he got lost. She'd be taking him every day, he got lost. Okay, so they don't pay attention, but so nobody thinks. So he sucked us in. All right? So he decided, so Samsung, they saw what was happening, right? And they started to just copy the thing like crazy, all right? And they were lucky, because then Google gave them this operating system that allowed us to actually deliver something that was close. If not, this thing would have been a monopoly, all right? And so I have a friend that worked for them here in the U.S. So it's not a U.S. company. And he said they kept telling them, they thought this was a fad. It was going to go. Nobody wanted to use a touchscreen thing. It's a fad. It's going to go. And they kept telling them, no, it's not a fad. You guys really need to do this. But they chose not to. But, part of it, though, they said, he says, my friend said, you have to be willing to self-cannibalize, right? Which is Kodak was not willing to do. You have to, at some point, you look hard at the stuff and realize what it is you're doing and see if you really need to change. Don't forget what you have to currently have. Those guys spent a lot of money on R&D, but could not convert into product. So, anyway, so these are, anybody knows who these guys were? Actually still around. No any guess? Good. And if you go to almost any other country now, they're probably one of the most popular phones. But these guys had everything to do what Apple did. Okay? But Dan couldn't do it. So, but it just comes back though to our thinking, right? You got to be thinking differently, and we're in that situation, I think, right? In terms of what is it going to look like next? We said, are millennials really want to order each of their meals separately, and they have to come delivered to the door? What does that mean for the system that we run? Do we need to think about it that way, right? And so. And I don't know to have the answer, but we have to really think about it that way. What is it really going to look like? So our approach is, we're trying to rethink it, and in terms of what we're trying to do. And looking at the integrated approach, looking at these as the significant drivers. And then we're trying as we can to create an environment where we work and with the people we interact with, to think about these things differently. What is it likely to look like, and how do we position ourselves to provide something of value? So these are our current research thrusts in the group. we have some interaction, you know, some teaming with various universities and industry, and we try to get government support where we can. So we have some work in agri-robotics, so we have some devices that actually working in the field, looking at different applications for agriculture. And then we have a huge effort as huge as it can be with the funding we have, looking at future poultry operations. And then we're doing technologies looking at food safety and the ability to track that and make sure that there are no issues. And just we're in a stage where we're trying to continue to figure out, you know, who we need to bring in, and then how do we kind of grow this so we are able to respond to the future challenge. Like I said, we've got to think of it as a system. And this is just meant to be a model. This is a model we have for using water in a processing facility. And the idea is, as we start to do development, you got to look at the whole system and look at interactions of different things and try to anticipate the potential issues before they happen, or as many of them as you can, right? It's hard to anticipate what's going to happen. Sometimes we do things and you don't know what, you have a benefit that you see, but you don't sometimes know the negative of it, right? So we're thinking that with proper modeling, maybe we can reduce that kind of impact. So this is a system we have for modeling water use in a plant, where you basically, you know, tell it how many products you're running, and then tell it something about the contaminant loading and so on. So this is, people here earlier explained a little bit about some of the stuff we're doing with the audio and the well-being of the birds. And so we have a project where we're actually recording audio in processing in growth environments. And then we generate these things. This is our first cut at it, called a GAMP, Growth Assessment Map. And looking at this, we can kind of tell several things. We can tell, you know, when night or when the lights are out. And you can see what happened here, it was going out, and then daylight savings time. So we're glad that showed up, right? It should have. And then you can tell different things that are going on in the house. You can tell when the birds were placed, and then when they left, and so on. But the idea is, you know, it might be possible to look at all these disturbances and then come up with some kind of a quantitative number that says, well, okay, you know, this is for the whole flock of birds. So this is 24 hours, and these are the days. And for the whole flock, nothing significant happened. So we'll score, give it a score of 90 because we didn't have significant, you know, occurrences in the thing. Or if there are more, then you give it a lower score. It might be a first cut at trying to figure out how you might actually try to, you know, assign a well-being score to animals that were grown in a rural house. And this is just kind of some of over here. Just again, people that work with us. Just a way of maybe presenting some of the data. As we're running along with the audio, maybe we have a data score and an overall score. And then from these things, people will be able to click them. And at that point in time, maybe they see a video or hear audio for what caused that thing to happen. So then they can make an assessment about whether or not they thought it was a significant issue. But this is just our thoughts right now, how we might try to move with some of this. So one of the concepts we have is something called a distributed testbed concept. And we actually now have started a sample project to try to implement that. So we're talking about the next generation of poultry and what that looks like. So one of the thoughts we have is, you know something? We think if you slaughter them on the farm, it gets rid of a lot of trouble. There's lots of animal well-being issues. People don't like to see them driving in the tractor trailers, right? If we could slaughter them on the farm, there are lots of potential benefits. And so what to be involved in doing that? So we actually started a project looking at this, right? And the idea is you'll actually, so you'll actually do not gas stunning, this is laps, lower atmospheric stunning. So you catch the birds out of the house like you saw on the previous one. You lap stun them in this device, and you put them in there, lower the pressure, and then they get stunned. And then you hang them in this device that would then go to this trailer. So then they'd hang in the trailer. Okay, here we go. So then there'll be a line in the trailer, and the birds would just go in there and they'd hang on these shackles in the trailer, and that's how they go to the plant. They bleed out in the trailer and then go to the plant. We're thinking, we'll have some robots here. But But that's the idea. Can you slaughter them on the plant? And this is looking at slaughtering them on the farm, and this is the next looking at the next generation way of doing it. And there's some potential benefits of doing this. So now it brings up a lot of questions. Bacteriological questions, right? Food quality questions. But to me, that's why we're here. Well, let's answer them. And so we have a joint project now ongoing with, so UGA is working with us, USDA ARS in Auburn. So this is actually us driving some of those birds in on our thing for an hour to see what kind of potential issues we might have. And then we actually did a study at Auburn where we allowed them to age for, 4 hours, which we assume might be the maximum time. You might drive them like that. And then these are folks working on doing the biologicals, trying to understand what are the potential impacts of trying to do this. So this is one of our thoughts about how we might take it in the future, right? Can you do, and then reduce what happens at the plant itself. Is this going to work? We'll see, right? But this is what I mean by a distributed test bed, though. So some of the work is going on at Georgia Tech, some of it is going on at UGA, some of it is going on at Auburn, some of it is going on at USDA ARS. So based on what's going on, you have different activities going on in different places based on the skills, right? And so we'd like to get NC State in on it. So the challenge, though, is, you got to figure out then who pays, right? It's not, none of the stuff is cheap. And so that's some of the things we're trying to figure out. How do you construct programs that allow you to tackle these types of things, which we think the university is well placed to do. These are the types of things we should be doing, looking ahead. And how do we get the support to do it so we can answer these questions? So, to do this, part of our job is how, we're trying to connect people, find out the people who are thinking differently about how to do it, look at what exists for technology and how you can adapt them, and then, how do we drive these things where we identify the solutions that we think are going to be necessary. And again, I keep saying this, we think most of those solutions are going to occur here. Right? You get engineering guys, you bring technology to bear, and you bring the knowledge of the biology together. And these interfaces, we think, is where we're going to be able to find some approaches to address these challenges that we're going to face. So you're never sure where it's going to go. So this project, Chick-fil-A came and said, I'm tired of these guys giving us bones and the meat. You have a way of trying to detect the bones. X-rays are too expensive. So we said, let's look at it. So we took a look at it, and we decided then, we had the idea, let's look at the frame after you've deboned it. So you do the cuts, you take the breast meat off, but you have the frame left. If the bones were left on the frame, there shouldn't be the meat. So we did then, let's look at the frame and see if we can see if the bones are still there, then that piece of meat will be okay, all right? And so we did it. Our accuracy was about 90%, and they didn't think that was enough. But then, we're looking at it and we're looking at this, but something, these blue things tell you about how much meat is left. And they were thinking about, how do I pay for this bone thing? I'm just going to have to buy these things. It's not going to give me any more yield. And so it's just going to cost me any more money anyway, right? Somebody said, that might be useful. If I could tell how much more meat is there, because we have to tell the yield. Well, what has happened is, that's the implementation we ended up with. It became a commercial product. They took it as a yield monitor. So GainCode took the idea, and they made this device called the yield scan. And so now they sell this device, and they put it on their lines to monitor yield, so they can monitor the line in time. So I mentioned that the cutter guys, after a while, they started not doing so well. But with this device, you can tell when it starts to happen, and you can swap or do different things. The other thing that happened is these companies are putting up these boards, and the lines are competing. Because your line stays green, I mean, you're doing well, right? And your line drops yellow or red. And so the lines are competing, boards and lines are competing. And so But the idea is we started out doing this one thing, and that's not where it ended up. And so we got to be ready for that too. Okay, we started doing this killing and processing on the farm. That might not be where it ended up. That might not be where the value is. But it's instructive probably to do it anyway, right? Because you might still get something valuable. So timing. Anybody into horse racing? You are. Does anybody know this race?
Oh, secretary.
On the rock. For the lead. On the inside, that time the line for the lead. On the outside, Shecky Green. Royal and Regal. And on the rail, it's Restless Jet. Followed by Our Native. Up on the outside is Gold Bag. Divide the stands for the first time. Shecky Green.
Secretary, way back here.
Royal and Regal. Now being moved to the inside, looking for room. Gold Bag is up on the outside. Then on the rail, it's Angle Light. Followed by Sham. Our Native, Restless Jet, Spy Gallant, then Forgo. On the outside, Navajo, followed by Secretariat, Warbuck, and finally, Twice a Prince. Moving on the turn, the leader is Shecky Green, leading by 2.5 lengths. Goldback in second by a head. Sham now third on the outside by 2 lengths. Royal and Regal fourth, 2 lengths, then back to Angle Light in fifth. Secretariat has made a sudden move and is now sixth. Then it's Restless Jet, Our Native beginning to move up. Navajo, Forgo, and Warbuck beginning to move up. Followed by My Gallant and Twice a Prince. There is the turn and launching forward with Shecky Green, still the leader by 1.5 lengths. On the outside and challenging is Sham, and he's now got it in front. Now Shecky Green responds to the challenge of those 2 ahead apart. Royal and Regal is third, holding on. Goldback drops back. Secretariat is fourth and moving up on the outside, and is now third, and moving out the leader to take up all the end of the stretch. They're at the end of the stretch, and Sham is the leader. He leads it by a length. Secretariat is the center of the racetrack and tracking. Shecky Green now drops back. Going on is Forgo, Our Native on the outside. Now on the stretch, it's Secretariat. Secretariat on the outside to take the lead. Sham holding in second. It's Secretariat moving away the exit by 2.5. Sham, then on the outside, Our Native.
Whose race was that? Derby.
This was the Kentucky Derby in 1973. Secretariat. So it went on to win the Triple Crown.
Right.
So he's the first horse. I think the only horse who every quarter he ran it faster. Usually most people don't do that, right? He's the first one you run pretty fast, but he ran every quarter faster than he ran the previous one. Okay? He won it. So the timing thing. Anybody know who Sham is? Sham came second. Well, here's the deal. He would have won any other Kentucky Derby. If he chose, ever since then, even till the last one, he'd have won any other Kentucky Derby. Except he ran with Secretariat. Okay? So timing is a heck of a thing. No, his was probably bad luck. but sometimes you just gotta, you know, you don't know when the timing is right? And you just gotta go for it. So we think the timing is right for a lot of the things you're talking about, right? The confluence of a lot of technologies. So you saw that picture I saw of the bird with the green thing, and I said it was a 3-dimensional part of the bird. So this was a camera that could do that about 5 years ago. We bought one. And you guess as to how much this guy costs? It's about the size of it. Well, you guys know what the Kinect looks like. It's the size, really. Have an idea? What do you think you guess that thing costs? About 5 years ago. How much? $1 million? That's a little high. It was $10,000. And so, they decided to make games for your kids. This device, same functionality. This thing had was only 100 by 100 pixels. This thing I had, 580 by 240, $150. So once the consumer market kicked in, okay, price. This guy, relative size is about the same, so this is the next generation stuff, okay? And it's still about $120. But still now, you're talking about the ability to sense those things for $100, right? If these guys now start to use all this stuff, and you start to make it for a car, right? It has to cause sense on a car for it to, you know, to be worthwhile for them. Then we're going to have a lot of technology we can build on, right, to tackle our problems. So that's what I mean by timing. I think the time is right now for us to try to do some of these things that I'm talking about, because a lot of things are in place. It doesn't solve the exact problem, but I can see how it all comes together to make some trackable solutions. So, you know, this is the group that supports us and, you know, advises us in our group, and we think it's going to take something kind of like this in terms of how we look at the future and where we go. You know, working with universities, industry, trade associations, and the government, right? We've got to figure out how we make this thing important enough to them that they think they want to do some investment. Because the one thing is the development is not cheap. The technology and the sensors are getting cheap, but really the cost, right, is just in the human capital you need to invest to build these things. It's really a costly thing. If you ask anybody that's built in a new machine and brought it to market, it's a significant investment in terms of time and resources. And usually it's not in the metal, right? It's usually just in the design and in the things you have to do. So what will it look like? You know, so this cartoon, yeah, we can get these devices to move things around, and they can calculate and do stuff, but in the end we don't want them doing this. Then you'll have a robot. So we think it might hopefully look something like that. So I knew you guys thought I did all that work. But I hate to blow your balloon, but there are a lot of people back there that do most of it. I just get to talk about it. That's it. Do you have any other questions?
Well, I've got one, and it's related to, since there are all these technologies, is what are the kinds of things in poultry production that are candidates for emerging technologies, and how do you prioritize that? Because some of these things we've been doing for ages, we just assume, okay, that's how you do it. But has anybody looked at, okay, what are the cost-demanding type activities or something that is hindering production efficiency that are candidates for that, and what is the economic impact or the cost of that problem, so that you know what you're willing to pay for a new technology, even if it's submarginal now, but knowing that that will improve later if you can just identify what are we looking for. So for instance, you're doing wing cuts, but if you're looking at poultry production, where are the problems that we should start thinking about?
Right, and so that idea of trying to look at the whole process again is trying to get at that. Because first of all, maybe we don't need to do it the way we've been doing it. Maybe there's some other ways to do it, and we should look at those ways. But to think about it. And part of the way we're trying to approach this, I show that water model thing. We're trying to see if you could model the whole process, and you assume you did something at a particular place, and it gave you this much benefit. Or what is the impact, right? Both in terms of environmental impact, in terms of economic impact. And then you might use those things and to evaluate different options to decide how you might best invest your money. That's not, it's a difficult question. But our thinking is, if you can come up with a model with enough fidelity, and you understand the process you're trying to implement. But you got to look at the whole thing. You got to look at it as a system. And then can you then start to figure out, if you did this here, what's the benefit on the end? And is that going to work, or is this going to give you a little bit more bang for the buck? But that's the way we're trying to go at it.
So my question follows up a little bit what Dr. Burkett mentioned. It has to do with the portfolio of research that is going on and there is impressive. And but the question becomes, according to this consortium of industry, university, government, all of the above, what are the inputs coming from these in terms of deciding that the composition of this portfolio compared to researchers and individuals in that group? So.
Yeah, and so that's always a tricky balance. Because so we have an industry advisory board, and they come once a year. They look at everything we're doing. And some of the things we see though, and you gotta be wary of it. A lot of them have different positions in the industry. And they tend a lot of time to come with a problem that they left the office with that morning. Okay, something broke. Well, you know, we need a research program to stop these things from breaking. You understand what I mean? So there's a balance you have to strike between, and some of those are valid things to look at. But then you'll never look down the road if you're constantly just looking at why something broke in this piece of machine. Maybe you should get rid of the machine. And so that's just so we've managed to balance it somewhat. Say, guys, you know, it's good to be trying to figure out exactly what this faucet needs to look like, but maybe we should look at some other things too. And so we try to balance it the best we can. But this, you know, it's a communication thing. And trying to, you know, you have to make the case that have the reasons for why you think you're doing what you're doing, and try to, you know, get them to understand, you know, why you think you ought to take that back. And sometimes they trust us, and then they say, well, you know, I really want you to figure out why that thing is broken.
All right, well, why don't we give a round of applause